Alright, the very last topic that we have to cover in Physics 20 is the Doppler effect. And all of you have dealt with this at some point. So if you've ever kind of seen an ambulance or a police car or fire truck, something with a siren pass by, you notice as it moves towards you, it sounds like the pitch or the frequency is really loud and really high. And then when it starts to move away from you, it sounds a little bit lower. So this change in frequency, or this what we call apparent change in frequency, apparent is the key word, is what we refer to as the Doppler effect. Now, we want to make the word apparent really clear. The frequency is still dictated by the source. So no matter if the police car is driving by you or like coming towards you or moving away, the frequency of the sound produced by the siren is always the same. That is dictated by the source, the actual siren. What we hear is going to change based on how fast it's approaching us, how fast it's moving away from us. So we want to be clear that it's the apparent change. The actual frequency of the siren itself is not changing. And we want to look at the case of, well, why does that frequency change? So we're just going to kind of look at we're going to just kind of move through this in a little bit of a hand wavy case. So let's look at a bug in a pond, and we have A and B equidistant from this bug. So let's say the bug bobs up and down, and produces these waves. Well, the person at A is going to receive the same amount of waves per unit time as the person at unit B. So if we get 5 waves per second here, B is going to find 5 waves per second. Not particularly interesting. So we want to get that bug to move. That's going to make it a lot more fun. Now, let's say that bug starts to move towards B instead. Still bobbing up and down, it's producing those waves, but now it's going to start to move towards B. What you'll notice here is that for B, these waves are bunching up. So what we're going to notice is that this wavelength is decreasing. So the wavelength is decreasing, but as it moves away from A, well, as it's moving away from A, these wavelengths are starting to increase. What that means is that as this wavelength decreases, what person at B is going to notice is they're going to have more waves hitting them per unit time than the person at wave A. They're going to receive less waves per unit time because they're so spread out. So because they're spreading out, fewer are arriving in the same amount of time as compared to the person at B. And keep in mind, how many waves arrive per unit time is exactly what we're talking about with frequency. So when this bug's moving towards B, it's going to increase. B is going to notice an increase in frequency of the waves because there's more waves approaching per unit time. Whereas at A, they're going to notice a lower frequency because there's fewer waves approaching per unit time. So A and B are going to notice changes in frequencies. What's important is that the bug's frequency of making those waves hasn't changed. That bug is still bobbing up and down at a particular rate. What A and B interpret is what they think the frequency is. The bug's true frequency has not changed. Now, there's some mathematics to this. We will not derive this. That is beyond the scope, or not beyond the scope, it's just not particularly interesting. So we have the following equation for the frequency due to Doppler shifting. So we have this F equals V divided by V plus or minus Vs times Fs. A lot going on in here. Let's look. So F is this apparent or Doppler frequency. So this is what you hear. So this is what you hear when the object happens to be moving. V without the subscript is going to be the speed of sound. This is usually given. Expect it to be in that 340 meters per second ballpark. Vs is going to be the speed of the source in meters per second. And then Fs, this is the source frequency or the true frequency. So for example, with the police car moving by, if on the siren it says, yep, this has a frequency of 10,000 hertz, that's what we call the true frequency. Now, we've put units here, but we can be really flexible. As long as the units on F and Fs are the same and V and Vs are the same, we can get away with different units. If you're ever unsure though, keep things in hertz and meters per second. Now, the one thing you may have noticed that's unique to this equation compared to everything else we've learned in Physics 20, you'll notice the lovely plus and minus sign in here. When to use the plus and when to use the minus depends on what's going on. So if the source is moving towards you, we're going to use the negative sign. If that source happens to be moving away from you, we are going to use the plus sign. This is something that you must be aware of. So we're going to look at a couple of examples of the Doppler. Alright, so we have an ambulance. It's a siren. It's making a sound at a frequency of 8.50 kilohertz while driving down the street. It's a cold day and the speed of sound is 300 meters per second. So that's very cold. So if the ambulance approaches at 25 meters per second, we'd like to determine the frequency we hear. If it's moving away at 25 meters per second, we'd like to determine the frequency we still hear. And we're going to determine the change in frequency. So you'll notice that we're not dealing with accelerating cases. Like the ambulance isn't accelerating, it's traveling at constant speed. That's just to keep the equation simple. If it's accelerating, that goes well beyond what we're prepared to handle at the high school level. So in part A, we are told that the ambulance is going to approach. So when we are being approached, what we want to use that negative sign. So we're going to have the frequency is V minus Vs times the source frequency. So approaching, we're going to have that negative sign there. So again, V is going to be, in our case, this is going to be the speed of sound. Vs is going to be the speed of the source. So our speed of sound, we're told, is 300 meters per second. And then we have 300 meters per second minus that speed of the source of 25 meters per second. And then we're going to multiply this by our source frequency, which we are told is 8.50 kilohertz. Now, for units, I have meters per second in here and meters per second on the bottom, so the meters per second will cancel. So in terms of units, I don't have to convert this because I have kilohertz here. All that's going to tell me is that my final answer will come out in kilohertz. This is why I was saying we get to be really flexible with the units. So we're going to get about 9.27 kilohertz when we approach. So when this ambulance approaches, we interpret the frequency as being 9.27 kilohertz. It goes up. That's what we expect. Now, when the object happens to be moving away, so we're moving away, this time our formula for Doppler, we're going to have that plus sign in the denominator this time. But the numbers that we plug in are still exactly the same. We're still plugging in 300 meters per second for our speed of sound. Just in the denominator, we're going to add them this time. And then we're still going to multiply this by 8.50 kilohertz. So same thing. The meters per second will cancel out. So because my source frequency is in kilohertz, I also want to have that my Doppler frequency is in kilohertz. And this is going to give me about 7.85 kilohertz. Now, we know when something's moving away, we expect the frequency to decrease. This is what we're seeing. We're happy with that. So then the final thing is we want to see what's that change in frequency. So we're just going to find the frequency of away minus the frequency of towards. Now, I'm going to use all the extra digits in my calculator to calculate this. So I'm going to have like 9.273 minus 7.846. So I'm using my unrounded values here. So if I calculate that difference in frequency, I'm going to get about 1.43 kilohertz. So between when the ambulance approaches you and starts to move away from you, what we're noticing, and sorry, I should have said F approach versus F away, not, sorry, I got it the other way. So what we're noticing is that that frequency change, it's going to be about 1.43 kilohertz. So there is going to be a change of just about 1400 hertz as the ambulance approaches versus when the ambulance moves away. So the last thing is, let's look at one more example. So we have a fire truck. It's moving towards an observer at 15 meters per second. So the apparent frequency of the truck siren, so what you hear, so this is the Doppler frequency, is going to be 1 times 10 to the 4 hertz. So we'd like to find the actual frequency of the siren. And we're going to assume that the speed of sound is 340 meters per second. So we are moving towards the observer, so it's approaching us. We want to use that negative sign in the Doppler equation. So we have F is equal to V minus Vs times the source frequency. What we want this time is, this is what we're looking for. We're looking for the source frequency. So the source frequency is going to be this apparent frequency divided by this V minus Vs. So the source frequency the Doppler frequency that we have observed is 1.00 times 10 to the 4 hertz, and then we're going to divide it by this lovely mess down here. So we have 340 meters per second, and then we are told that this object is traveling at 15 meters per second. So let's see what we got going on here. So we're going to get about 9.56 times 10 to the 3 hertz. So this is my actual frequency of the source. So this is what's actually printed on the object producing this noise. So its frequency is about 9.56 times 10 to the 3 hertz. So let's check. As something approaches, we have an increase in the frequency, which is what we expect. So we can be pretty confident in our answer. With Doppler effect, make sure you're distinguishing between the actual frequency and the Doppler frequency. People mix those up all the time. And with that said, that is the end of Physics 20. So you've learned everything you need to know for this course to say you're done and to move on to Physics 30. So my fullest congratulations to you on getting to this point. Job well done.